Hello everybody, welcome to our webinar about the KNIME Image Processing extension. My name is Christian Dietz. I'm here with Martin Horn from the University of Konstanz, and today we will give you an introduction what the KNIME Image Processing extension is, why we use KNIME for image processing. We will give you a short live demo with a high content screening workflow as an example. And afterwards, I will tell you a little bit more about our collaboration with the ImageJ2 team of the University of Wisconsin in Madison. First of all, for those who don't know KNIME yet, I will just briefly give a brief introduction. KNIME is a workflow-based tool, and what you see here on the slide is basically such a workflow. A workflow is composed of so-called nodes, which you can see here, and those nodes are connected via these wires to other nodes. So for example, what you see here is the Excel reader node. It reads in an Excel file, then it combines this data with some data of the database in the joiner node, and then it converts something, string to date time, and does some more stuff. And those bluish nodes, which are so-called views, you can have a look at your data and write data out again to the database or on your hard disk and so on. In the case of image processing, you can imagine that you have a so-called image reader here. You combine images from several sources, maybe, and then you can do some pre-processing on the images, then you do some segmentation, then you do some feature extraction, and then you have some statistical analysis on the results of this feature extraction. Okay, that's KNIME. So KNIME is a workflow-based tool. So why do we do image processing in KNIME? Well, there are a lot of tools out there which can be used, which are great for image processing. And for certain tasks, you would need a certain tool. Okay. So one reason why we use KNIME is that we want to integrate those tools and those frameworks. So we want to have one integration platform, which is KNIME, where you can use many of these tools, not all of them, which are listed here, but many of them together in combination. But not only these tools, so you can also then combine the image processing stuff with, for example, machine learning, like Vika, like R, like other nodes which come with KNIME for some data mining, pattern mining, or something else. Then you can combine it with other domains like chemoinformatics or text mining and network mining. So KNIME can be seen as an integration platform where you can combine several areas or different areas, various areas, and bridge the gap between them. Okay? So is KNIME only good for integration? Well, no, there are a lot of more features which we can use in our KNIME image processing extension, which come along with KNIME, for example, the data caching. Imagine you have millions of images which you want to process. So KNIME takes care that your working memory is not overloading, and this means that KNIME reads in data from your hard disk whenever it's needed, but if it's not needed anymore in your workflow or it's temporarily not needed anymore, it will be written on your disk. So there's no problem that your memory is getting full. Another advantage is the fast prototyping. For example, you want to create a new or compose a new algorithm consisting of several basic functions like difference of Gaussian, for example. Then you take two Gaussians and then you subtract them and so on. And things like this you can easily click in KNIME. This means you have a graphical programming engine which you can use to compose new algorithms, new workflows without even writing one line of code. Of course, KNIME is very good for automation. So again, you have millions of images which you take with a microscope at night, and then automatically, for example, a KNIME workflow is executed after the images are taken and the analysis is run. And later you get a report where you can see all the statistical results of the KNIME analysis, KNIME workflow analysis. You can even do more automation. For example, imagine you have a microscope which sends the images directly to a KNIME workflow. Then the KNIME workflow sees, oh, there's something interesting on this image, or there's nothing interesting, but let's say there is something interesting, and then the KNIME workflow gives feedback directly to the microscope. The microscope then, for example, takes a more detailed image, let's say a 3D image, and sends it back to KNIME. Then KNIME decides, oh, it's a 3D image, I have to do another analysis, and so on. So KNIME can provide feedback for the microscope. Something else you can do is the interactive data exploration. If you have tons of images, you can create histograms, scatter plots, and so on. And then you see, let's say, a group of outliers in the scatter plot. Then you can mark this group using the interactive highlighting of KNIME. And then this highlighting is also reflected in the images. So you can see the cells, which are the outliers in the scatter plot in the images. You will see an example later in the live demo of Martin. And of course, what I already mentioned is you can combine image processing with machine learning. So you can classify, cluster, and so on your image data or the results of your image analysis. And of course, you can bridge domains. This means you have a hit found in images, and then you want to see the chemical structure which caused the hit or something like this. Now we come to the KNIME Image Processing universe. So, of course, we have our KNIME Image Processing Core plugin, which you see here, which is in version 1.1.2. And there we have a lot of nodes and a lot of functionality for image processing. And all these nodes you will see later in the live demo of Martin. What I want to show you here is the libraries we use to develop our KNIME Image Processing framework. So, for example, we heavily use SciJava, which is a project which came up during the ImageJ2 development in Madison, University of Wisconsin. Then we use ImageJ2, we use some ImageJ1 functionality. We heavily use imclub2, which is the basis also for ImageJ2. We use VTK, we use CFO, we use Omero, and so on. So we don't want to reinvent the wheel. We really use what's out there and combine it and integrate it into KNIME, okay? For example, the ImageJ 3D viewer, we just use the Fiji plugin 3D viewer, adapted it a little bit, that works in KNIME, and we have it running. So you can inspect 3 to 5 dimensional images in KNIME. For tracking, we use TrackMate of Fiji. Some of you may know the plugin. It's a very, very nice plugin, and you can use any segmentation algorithm in KNIME or any feature filtering in KNIME, and then use the standard TrackMate tracking algorithms in KNIME. We have optical character recognition. A simple Java wrapper for tesseract OCR is test4j, and imagine you have, for example, an image containing text, which is containing text, and then you want to extract the text from the image so that you can further process the data with, let's say, text mining algorithms. And there we have one node, the test4j integration. Then we have this nice new thing, which is currently experimental. It's called supervised image segmentation. Supervised image segmentation can be compared to the Fiji trainable segmentation plugin, but it's nearly the same, but not the same. So what you can do, what you also can do in the Fiji trainable segmentation plugin, is that you mark some images with a ground truth. So you say, hey, there's a segment here, there's a segment there, and there's a segment there. You really mark the segments, then you train a model, and then this model can be applied to images which are not segmented yet. Okay, that's the basic idea behind this supervised image segmentation, which is an output from the PhD of Martin Holm. Then we have this Omero integration. So we have an Omero reader which can be used to read in images from Omero image database, and which then can further be processed in KNIME. Okay, so there's a lot of more functionality. You can see all our plugins on the KNIME website, on our website, which is tech.knime.org community image processing. There you find our update sites. You find details about installation, how to install KNIME image processing. Then you find some news. You find a wiki, GitHub links. So our code is open source, and you can find it on GitHub. Then you find our forum and our contact information. We want to encourage you to use the forum if you have any questions, because then everybody can benefit from your question and from the answer. But you can also email Martin or me, you find our contact information on the website. What you also find on the website is are a lot of example workflows and tutorials. There you can see how you can use our nodes and what you can do with KNIME Image Processing. Now Martin will give a live demo. He will present KNIME Image Processing with an example workflow for high throughput screening. And after this live demo, I will give you a short overview about our collaboration with ImageJ and ImageJ2.
In the live demo, first of all want to introduce the image data type, which comes with the KNIME Image Processing extension. We call it IMG plus cell. And then I want to demonstrate important image processing, image analysis tasks by means of a high content screening example. So let's switch to KNIME. For those who are not familiar with KNIME yet, this is the KNIME workbench where you compose your workflow and connect the nodes together and so on. This is a KNIME Explorer where you find all your workflows you already created. And this is a node repository where you find all the nodes that are available in KNIME currently in your installation. You can add a node from the node repository to the workbench just by dragging and dropping them onto it and then connecting it to other nodes. If you install the KNIME Image Processing extension, then there will be another category within the community node category and called KNIME Image Processing, and here you find all the nodes which come with this extension. For instance, node to read and write images, to process images, to do segmentation, calculate features, and so on. Some of these nodes I'm going to show in this live demo. The first step of an image processing workflow is, of course, usually the image reader to get images into KNIME. I have here one image reader. Each node, if you click with the right mouse button onto it, has a so-called context menu, and there you find, for instance, the possibility to configure the node. In the case of the image reader, you can select the image files you want to read. I already have selected some. Okay, and then afterwards you just execute the node, and then the node is executed. And in this case, the result of the node is a data table. Is a data table with one column which contains all the images that we have selected in the image reader. Now it looks a bit strange because some of the images are just black, but the reason is that these images are not normalized. So to normalize the images, we can just use the image normalizer node. You can search here for certain nodes. Image normalizer, we drag and drop it on the workbench, connect these two nodes, and configure. Many nodes of the image processing extension come with a so-called column selection, where you just select the column you want to process, and you select a certain mode how the result will be created. For instance, you can either create a completely new data table, you can append the newly created results as a new column, or replace the currently selected column. Here we choose, for instance, append, and we add a suffix to be able to distinguish the result from the other one. Execute the node, and now the images are getting normalized. So let's have a look at the result table, and here now you can see that there are not the images are not just black, there is even more. So now in this view the images appear to be two-dimensional, but this is actually not the case, because if you have a closer look on the metadata on the images, you can just switch here the renderer. Then you immediately see that almost all of these images have just had more than 2 dimensions. For instance, this image has already 4 dimensions: X, Y, Z, and time. This has even 5 dimensions: X, Y, channel, Z, and time, and so on. And the second thing you may recognize here is that the images have different pixel type. This, for instance, is unsigned short type. This is an unsigned byte type, and this just means this just tells you what values a pixel can have in this image. An unsigned short type, for instance, a pixel value can range from 0 to 65,000. In an unsigned byte type image, the pixel value can range from 0 to 255. Now, in this view, it's very hard to inspect this multi-dimensional image data. That's why almost every node in the image processing extension comes with a so-called table cell view. We just open it, and then you have here on the left side again your data table. And if you now click on an image you want to inspect in more detail, then it appears on the right side, and here you have much more options to explore your image. For example, zooming in, zooming out, scrolling through the different dimensions, normalizing your image here with some saturation, changing the renderer, for instance, to render RGB images in color, some image properties, and so on. And you can also hover over the image to inspect individual pixel values. Okay, that's so far about the basic image type. Let's switch to the example workflow I've prepared. So the task of our example workflow is first of all to segment cell images, that is to identify the individual cell on cell images, and then to classify them whether they are positive or negative cells as depicted here. The experimental setting is a 96 well plate where each single well is represented by an image, and for the columns here a different dose of a certain drug was added to the image, resulting in a different amount of negative and positive cells. And the aim is of course to count for each single well the number of positive and negative cells, and what tells us what are positive or negative cells are the ground rows in the first and the last column. More details about the dataset and the biological background can be found here. So back to KNIME. This workflow of course also starts with an image reader where we read in all the images we want to process, and we get a data table with all the images, 96 images. They are colored in red and green. Red represents the nuclei channel and green the cytoplasm channel. And usually after you read in your image, you want to pre-process it somehow, for example, converting it between different pixel types using the image converter, normalizing the image, and many things. Or here in this case, we want to correct the illumination, the kind of background correction. Because if you have a closer look on some of these images, you might recognize that if you increase the saturation here, recognize there's a little bit a distribution of background intensity, especially on the right side there are some artifacts. Here you can see it quite well. And we want to get rid of these uneven background distribution. To do so, we we average over all our images and generate a mean image, and then divide every single image by this mean image. Let's just do it. By the way, these nodes here are so-called meta nodes, and these are actually just sub workflows, and they help you to organize your KNIME workflow to be able to deal with the complexity of some workflows. To go into such a meta node, just double click on it and you're here. So what I said, we first of all want to create a mean image. That is, we want to group our images. That's why we use the group by node. Here we don't have to select any column because we want to group all images and don't need a column which specifies that there's certain groups. And we want to group all of the images, and we want to have the mean image. Execute. So as this node is a KNIME standard node, it doesn't come with the table cell view, but that doesn't matter because there is this table cell viewer node which exactly provides the table cell view, and with this node we can have a closer look on our mean image. Let's normalize it, and it looks like this. Now, before we divide our images by this image, we may want to smooth it a little bit by using the Gaussian convolution node, for example. We choose, for example, 40 as sigma and run it. And now our mean image looks like this. And this is actually what we expect, that we have a higher average intensity on the right side of our images. So now we want to divide our original image by this mean image. To do so, we first of all have to put the mean image and the original image into one table back again with the cross joiner. This, in this case, essentially just appends the mean image to each source image, and we get a data table like this one, our original image and the reference to the mean image appended to each of this. So now the division. Therefore we have this image calculator which allows you to apply arbitrary arithmetic operations on images. In this case it's quite easy. We want to divide our image by the mean image. Now we expect, of course, that the division gives us floating type pixel values, so we choose as a result pixel type float type, and we want to create a new data table with a column called image where we write our results into. And for the further process, we don't want to work on the float type image because it's quite big. That's why we convert our float type image into an appropriate pixel format. Let's choose unsigned byte type, and at the same time we also want to normalize and scale it, so you immediately see what the result is then. And now back again we have our normalized or our background corrected images. The effect is not very strong, to be honest. You can't see it here quite well, but if we have a closer look, on some of these. So this distribution is less probably. But anyway, the main purpose is to show you some nodes and what nice things you can do with it. Now, after we have corrected our images, we want to segment, we want to identify the individual cells on our images, called segmentation. And if you have a look again on these two images, as I said, there is one channel with nuclei, another channel with cytoplasm, and we want to apply different segmentation methods for each single channel. Here we want to do a global thresholding, and then using the segmentation result of the nuclei to segment the cytoplasm by a region growing algorithm. As we want to treat these channels differently, we have to split them first with the splitter node. The splitter node, there you have to select the image you want to split, the image column, and the dimensions which should be remain together in your result. So here we want to keep x and y together, and all the other dimensions are going to be split. In this case, we only have one third dimension, which is the channel. If we execute them, the result table then contains two columns with the two channels. So now we can work on the channels individually. So as I said, we want to threshold the first channel. There we have this node global thresholder, and there we select a certain thresholding method. You can also select the manual threshold and specify a threshold manually, but here we choose an automatic global thresholding method, and also works quite well in this case. And important here, we only want to threshold the first column, the first channel, and we want to replace it because we want to still keep the second channel in the same data table. And the result is then this column. This column contains now images, but these are bit-typed images, so each single pixel has either value 1 or a 0. But what we wanted to have is a segmentation, and this is not a segmentation yet. And we want to make one of it a segmentation. So what we want to do is actually identifying all connected components, all pixels that belong to one blob. And therefore we have the connected component analysis node, which exactly does this, identifies connected components. And we want to treat the pixel values of 0 as background. And the same here, we only want to do it on the first image and want to replace this column. And then we have, let's have a look on it with the table cell view. And then we have our segmentation, which is represented as something we call labeling, because each pixel is now labeled. Such a labeling is actually nothing else than an image. It can also be n-dimensional and so on, with the only difference then that instead of real values for each pixel, here each pixel receives a label. This can be an arbitrary string. In this case, the labels are also numbers, but these numbers are actually strings. And important is that pixels of the same label are now treated as belonging to the same segment. As for example, these pixels with label 124 are all of the same segment. And of course, pixels with the same label get the same color. Now we want to use this segmentation of the nuclei also to segment the cytoplasm. with a region crowing algorithm. We choose the raw noise segmentation. This is a region crowing algorithm which starts growing from certain seeding points. Our seeding regions is our nuclei segmentation, and we want to do it on the second channel. That's why we select the second column here. And we have to specify a threshold where the region crowing should stop. In this case, 20 turned out to be quite a good choice. And we just want to get a segmentation without our seeding points. Okay, this takes a while. While this node is executing, run remark on the result of the thresholder. Here, of course, you could, if we have a look again on our thresholding result, here we could do some more post-processing, because there are small artifacts here, like this one we actually want to get rid of. To get rid of these little dots, you can either use morphological operations, which you'll find in the binary category of our image processing tool. This run morphological image operating like open and close, or which is also quite nice, you can use a labeling filter. Labeling filter after we have identified the correct components, and just filter out very small segments. Let's say segments that don't have more than 10 pixels. And then you get also rid of the small segments. Okay, the result of the region crowing algorithm is now a nice segmentation of the cytoplasm, as shown as here in the third column. And now we have actually all in place to do a feature calculation, because we have the segmentation of our nuclei, we have a segmentation of our cytoplasm, and we have the source image where we want to measure some things or calculate some properties on. So let's go to the next step, the feature calculation. In the feature calculation, we actually calculate certain properties for each single segment, for each single cell, for certain reasons, either to filter them, or in this case, as going to show you, to characterize them by numbers to be able to classify them. To calculate features, there are these feature nodes here. We choose the image segment features because we want to calculate our properties based on both on the segmentation and the source image. Configure the node, and then we have to select a labeling, a segmentation we want to work on. Let's first of all work on the cytoplasm, and a source image. We just have one source image to select here. And as features, we choose very basic first order statistics and maybe some segment geometry features like number of pixels, or let's say area, the singularity, and the parameter for example. Let's run the node, and now for each single segment and the corresponding area in the source image, these features are calculated. We want to do the same also for the nuclei. That's why we just select here the nuclei segmentation, and I uncheck this. I explain it later why. And want to join these two data tables to just one table. And what we get is another little bit larger data table which has 16,000 rows, and each row represents a segment of our source labeling. With the features we have calculated appended here. Here are all the features of the cytoplasm and the same features for the nuclei. And additionally, for the cytoplasm segmentation, there is also some additional information like the bit mask of each segment, the label of the segment, and a reference to the labeling where this segment comes from. These three things are mainly important if you want to recompose, as I'm going to show you in a minute, recompose you from this data table again labeling a segmentation. I quickly show you what I mean with this. So, for example, if you want to filter this data table according to a certain feature, let's say the mean value, and then recompose your labeling with based on this filter table. So let's first filter. Filter our data table. Let's say we only want to have those segments that have a mean value not lower than 30. And we get a data table with less. Okay, to make it a bit more clear, let's choose 40 here. And we have a quite small data table with only 4,700 segments remaining. And now for some tasks, you might want to compose these data table again to a labeling, to a segmentation. And this is done by using again the group by node. And we want to group according to the source labeling. So we want to have segments that came from the same source labeling still in the same segmentation. And we want to group all bit masks and compose a labeling out of them. And if you choose the compose labeling as aggregation option, then you can also specify some additional parameters like the size of the resulting segmentation, the label each single segment should have. We just choose label. You can also choose another column, of course, here, and so on. And we get, this is again a reference to the source labeling, and here we get our composed labelings, but with all segments that have a mean intensity lower than 40 filtered out. But this just as a side mark. Okay, now as we represented our segments as a list of numbers, as a vector, we can now nicely apply, for example, machine learning methods. And that is what we want to do, because we want to classify the segments into positive and negative. And I already prepared this step because it's actually out of the scope of this webinar, but just briefly. For classification, you need a training sample, and here it comes with the data set we're using here. There comes a data file which contains the well plate design of the well plate I showed you previously, and there you can get the information which images of which column and row are negative controls, positive controls, or which are unknown, so which have to be classified. And from this information we can assign to a certain set of segments already a label, because for some of these cells we know that they are positive and negative because they are coming from a positive or negative control image. And after doing this, we get a training set with almost 4,000 segments which have a label, either -1 or +1, negative or positive. And we can then use this training set to create a classification model. Here in this case we use a decision tree. And this classification model, based on learned or created only based on this 4,000 segments, we can then do a prediction for the so far unlabeled segments, which is done with the decision tree predictor. And this decision tree predictor now returns a prediction for each single cell. And this is what we wanted to have. So this information, this classification can of course further be used in KNIME standard workflows to explore the data, to visualize the data, and so on. Here, just as a very simple example, we can plot the counts of positive and negative cells for each single image and visualize it in a line plot, as shown here. And then here you can see that, for example, with the increase of the dose of a certain drug, the number of positive cells decreases and the number of negative cells increases, for example. But this is just as a very basic example. And another nice thing to do with one important note I want to show you is you can how to explore and how to verify your segmentation result and your classification result visually by using the images and the segmentation. And to do this, an important and useful node is the so-called interactive segmentation view. And this node essentially takes a segmentation column and an image column and overlays them. And then with this you can more easily see if the segmentation result or the classification result fits your needs or satisfies your expectations. So this node provides a view, an interactive segmentation view. And with this node, for example, we can have a closer look on the segmentation result overlaid of the classification result overlaid on the source image. Let's change the color a bit. Here. And the blue cells are the negative ones, the others are the positive ones. And now you can inspect and verify if the classification really is as you would expect it to be. Is there an image with more? Yeah, here quite a lot of positive cells, for example. Here many negative cells and so on. But what this interactive segmentation view also allows is it supports this highlighting mechanism. It's a very basic and a useful feature of KNIME. And to demonstrate it, I open here a scatter plot. a scatter plot showing some where you can plot certain properties of the segments, let's say the mean of the segments and the standard deviation of the segments. And now you might want to be interested in the outliers here and want to see them in the original images, because yeah, you want to visually see them on the images. And to do so, you just select highlight the selected points here, and at the same time we open the interactive segmentation view, and these cells we have highlighted in the scatter plot are also getting highlighted in this view. To make it better visible, let's turn the highlight mode on, and then here, for an example, these are the outliers we have selected in the scatter plot. And of course this also works the other way around. And in this view, for example, you can also filter segments out that you selected here, and there are a lot of other things you can use here, you can do here. Okay, that's all, and that's the end of the live demo.
So after this nice live demo of Martin, I will now talk about our ImageJ integration. We have a collaboration with the team of the University of Madison in Wisconsin. And first of all, I will show you what we have concerning the ImageJ1 integration. So as many of you might know, ImageJ and Fiji are very popular and highly interactive image processing tools. And the real strength of ImageJ and Fiji comes from the tons of available plugins which can be used in ImageJ. So if you have an algorithm and you want to use it in ImageJ, it's very easy and convenient to write such an algorithm and plug it into ImageJ, or send the algorithm via email to somebody or something else. And we can use these plugins and ImageJ and Fiji in particular in our ImageJ macro node. So this means if you want to run your own ImageJ macro in KNIME, you can simply copy paste it into this macro node configuration and run it. We support out of the box some predefined macros like Gaussian convolution, like watershed segmentation for cyclone splitting, or Clahe contrast enhancement, and so on. But you can also plug in your own stuff there. ImageJ2, this is the next generation of ImageJ. ImageJ2 is developed at the University of Wisconsin, and it's a complete redesign of ImageJ, but it's still fully backwards compatible. This means everything which worked in ImageJ1 also runs in ImageJ2. And one very important fact is that ImageJ2 bases on imclip2. imclip2 is a programming framework for image processing to access data, to access pixel information, and so on. And also KNIME uses imclip heavily. So this is a very nice thing, because then we can have a very easy way to integrate our stuff on a development level. So what we already can do is, if you have an ImageJ2 installation, you can automatically create from ImageJ2 plugins KNIME nodes. So as long as your ImageJ2 plugin is headless, this means it doesn't need any user interaction besides the configuration dialog, we can automatically create a KNIME node out of it. Okay? The cool thing is, if you write your own ImageJ plugin, you can install it in KNIME and the node will magically appear. So you don't have to know the details about KNIME implementations. You just can use the ImageJ2 plugin mechanism and use then the algorithm, the plugin, as a KNIME node. So what is work in progress? KNIME and ImageJ, we want to be able to run workflows in ImageJ. So you create your own KNIME workflow, then you wrap it as an ImageJ2 plugin, upload it maybe, and then it's automatically wrapped. And then you can run the workflow headless in ImageJ2. So you will never see KNIME. It will be like an ImageJ2 plugin. Okay. The other thing is that we want to record workflows. You know, the macro recorder. So what we want to do is, if you click on some basic image processing steps like smoothing, then binary, thresholding, and so on, then you will get a KNIME workflow out of it. So it protocols what you are doing. It's documenting what you are doing. And then you can hand this workflow via email to a friend or to some researcher who also wants to use it. Okay, what about ImageJ in KNIME? We have this node creation stuff from ImageJ2 plugins, but we also want to use the ImageJ2 update site. Like in Fiji, you have this update site where you can update your Fiji distribution with plugins, and exactly the same plugin site we want to have in KNIME, such that you can enhance your KNIME image processing extension with plugins you want to see in KNIME. Okay. And of course, we have recently we started a new framework. It's called ImageJ Ops, which will be a common framework for image processing algorithms. This means ImageJ2 needs implementations for algorithms, KNIME needs implementation for algorithms, any other tool needs implementations for algorithms. So we thought, why should we reinvent the wheel over and over and over again? Why don't we have a common framework for image processing algorithms where we share all our functionalities? Okay, and we started this program or this framework 2 weeks ago in the hackathon in Konstanz with the ImageJ2 team. Johannes Schindelin and Curtis Reeden were here in Konstanz, and we worked 1 week heavily on this topic. So the ultimate goal of KNIME and ImageJ2 is a full bidirectional integration. We want to run KNIME in ImageJ, and we want to run ImageJ in KNIME. So that's why it's bidirectional integration. Just one more slide, a little outlook. So what we will do in our next release, which is 1.2.0, we will have a new image writer node, which uses Sifio ImgSafer. We will have a new image segment feature node, so that you can calculate more statistics on your segmentations, like hue, moments, unique features, more shape descriptors, and so on and so forth. We want to have a better support for color tables, and we want to support single file huge images. This means since now we can process millions of images, but if we have one image which is larger than your actual working memory, we have a problem. So thanks to Sifio and Mark Heiner from Sifio, there exists a framework for that, and we want to integrate the framework such that an image can be larger than your working memory. It can be 1 terabyte or something, and all our algorithms still work. And of course, we want to go on with our collaborations with ImageJ, the guys from Dresden, ImgLib, Fiji, and so on, about operations, algorithms, region of interests, and so on. Thank you for your attention, and if you have any questions, I think now is a good time to ask. Thank you.